In geometry, we often need to reconstruct a given segment at a point along an arbitrary line. So I have an arbitrary line and I want to essentially move a segment down. So we use the term congruent segments to designate segments with the same length. And we denote it by this symbol here, which is just read congruent. So now I'm going to look at a few different ways we can actually do this kind of congruent segment and construct these. And while I will not prove these, if you're curious, you can absolutely look up the proofs or try to prove them on your own. I'll start with what's known as the segment construction theorem. The segment construction theorem says if I have two segments, we'll say AB and CD, where AB is less than CD, so CD is longer. Then we have a unique segment CE that may be constructed on segment CD congruent to AB. Essentially what that says is I can find a unique point E on this segment such that the distance between C and E is equal to the distance between A and B. So this is our first segment construction theorem. For my next construction theorem, I need to introduce an idea of a midpoint. If we have a point M that lies on a given segment AB, such that the distance between A and M is equal to the distance between M and B, then we call M the midpoint of segment AB. And if we have any kind of line, ray, or segment that passes through this midpoint M, it is said to bisect the given segment AB. So now that we have that, let's look at our next construction theorem. Not surprisingly, since I just defined the midpoint, we're now going to find the midpoint construction theorem. The midpoint construction theorem says that the midpoint of any segment both exists and is unique. So no matter what, if I have any kind of segment, I can always find the midpoint and refer to and talk about the midpoint. The next one is the segment doubling theorem. My segment doubling theorem says if I have some segment, AB, whose length is less than alpha over 2, then if I think of the ray passing through A and B, there exists some point C such that B is the midpoint of segment AC. So essentially, I can always double the length of a segment, provided the length was less than alpha over 2. And that's just designed to prevent the fact that I can't have a segment with length greater than alpha. So I always have to make sure I never go over alpha whenever I double. Before I do my next theorem, I need to define an extension. If I have the betweenness relation ABC, then my segment AC is called an extension of the segment AB in the direction B. Equivalently, you could say it's an extension of the segment BC in the direction of A, but essentially I have a segment and I'm just going to extend it out in one direction. So now let's define our segment extension theorem. The segment extension theorem says any segment can be extended in either direction to any desired length less than or equal to alpha. Our segment doubling theorem said we could absolutely double the length, but the segment extension theorem says that I can actually extend it to any length as long as it's less than alpha. When looking at our segment extension theorem, one thing we actually need to consider is how can it be shown that this situation right here cannot occur, that we can't extend it in multiple ways. So essentially, how do we know that there's only one extension rather than something like this? So I'm not going to give you the direct answer here, and I encourage you to try to think about this. Try to see if it would come into direct conflict with any of the previous results that we know of. Your intuition should tell you that this is impossible, and it absolutely is. But try to see if you can figure out why. This is actually known as the uniqueness of opposite rays. There exists exactly one ray that is opposite any given ray. So essentially the idea here is I have array BA. It should be opposite BC or BD, but it should be unique, which is not the case in this picture here. So try to think about why that's impossible. Why is it that we can only have one of these?